Hello everyone, my name is Feng Zhang. I'm going to present our recent work on fine-grained window-based stream processing on CPU-GPU integrated architectures. This is a joint work of Renmin University of China, Technische University Berlin, National University of Singapore. This is the outline of our presentation. Next, I will introduce the background. First, let's look at two important concepts in stream processing: bulk synchronous parallel model and continuous operator model. For bulk synchronous parallel model, it is conducted on the query granularity, where the whole query with multiple operators on each batch of input data is dispatched on one device. SABA is an excellent work from Sigmod 16 and takes this model. Such a mechanism naturally minimizes the communication overhead among operators inside the same query. It is hence suitable in discrete CPU-GPU architectures, where PCI-e overhead is significant and shall be avoided as much as possible. For continuous operator model, it is conducted on the operator granularity, where each operator of a query can be independently placed at a device. Please note that CPU and GPU can concurrently execute in both cases, only the granularity is different. Previous research mainly takes bulk synchronous parallel model. However, we found that continuous operator model is also useful, and particularly, it is very suitable for integrated architectures. The integrated architecture usually consists of a CPU, an accelerator such as GPU, and a shared memory. In 2011, AMD releases its integrated architecture called APU. Next, Intel and NVIDIA also release similar integrated architectures. Compared to the discrete CPU-GPU architecture, both CPUs and GPUs are integrated on the same chip. The most attractive feature of such integration is the shared main memory, which is available to both devices. The integrated architectures have no PCI-e transfer overhead and have shared global memory and high energy efficiency. We show a comparison between the integrated and discrete architectures in this table. These architectures are used in our evaluation, although the integrated architectures have low computation capacity than the discrete architecture currently. The integrated architecture is a potential trend for a future generation of processors. Moreover, its price and power are usually low. We consider supporting the basic SQL functions with stream processing, as shown in the figure. SQL on stream processing consists of the following four major concepts: data stream, which is a sequence of tuples. A tuple is a finite ordered list of elements, and each tuple has a time step. Window, which refers to a finite sequence of tuples, which is a data unit to be processed in a query. The window in stream has two features: window size and window slide. Window size represents the size of the data unit to be processed, and window slide denotes the sliding distance between two adjacent windows. Operators, which are the minimum processing units for the data in a window. In this work, we support common relational operators including projection, selection, aggregation, group by, and join. Queries, which are a form of data processing, each of which consists of at least one operator and is based on windows. Additionally, note that in real stream processing systems, such as SABA, data are processed in batch granularity instead of window granularity. A batch can be a group of windows when the window size is small, or a part of a window when the window size is extremely large. Now, let's look at the motivation. We analyze the operators in a query and find that different operators show various device preferences on integrated architectures. Some operators achieve higher performance on the CPU device, and others have higher performance on the GPU device. We use a simple query of group by and aggregation on the integrated architecture for illustration, as shown in the slide. The GPU queue is used to sequentially execute the queries on the GPU, while the CPU queue is used to execute the related queries on the CPU. The window size is 256 tuples, and the window slide is 16.4. Each batch contains 64,000 tuples, and each tuple is 32 bytes. The input data are synthetically generated, which is described in our paper. When the query runs on the CPU, group by takes about 18.2 microseconds, and the aggregation takes about 5.2 microseconds. However, when the query runs on the GPU, group by takes about 6.7 microseconds, and the aggregation takes about 5.8 microseconds. We further evaluate the performance of operators on a single device in the table. This table shows that using a single type of device cannot achieve the optimal performance for all operators. The aggregation includes the operators of sum, count, and average, and they have similar performance. We use sum as a representative for aggregation. From the table, we can see that projection, selection, and group by achieve better performance on the GPU than on the CPU, while aggregation and join achieve better performance on the CPU than on the GPU. Additionally, projection shows similar performance on CPU and GPU devices. Specifically, for join, the CPU performance is about 6 times the GPU performance. Such different device preferences inspire us to perform fine-grained stream processing on integrated architectures. Based on this analysis, we propose our key idea, fine-grained stream processing. A fine-grained stream processing method that can consider both integrated architecture characteristics and operator features shall have better performance. First, co-run the operators that do not reach the memory bandwidth limit. Second, put operators on the preferred devices that can bring more performance benefits. However, enabling fine-grained stream processing on integrated architectures is complicated by the features of SQL stream processing and integrated architectures. We summarize 3 major challenges as follows. The first challenge is application topology combined with architectural characteristics. Application topology in stream processing refers to the organization and execution order of the operators in a SQL query. First, the relation among operators could be more complicated in practice. The operators may be represented as a deck instead of a chain, which contains more parallel acceleration opportunities. Second, with architectural characteristics considered, such as the CPU and GPU architectural differences, the topology with computing resource distribution becomes very complex. In such situations, how to perform fine-grained operator placement for application topology on different devices of integrated architectures becomes a challenge. The second challenge is SQL query plan optimization with shared main memory. First, a SQL query in stream processing can consist of many operators, and the execution plan of these operators may cause different bandwidth pressures and device preferences. Second, in many cases, independent operators may not consume all the memory bandwidth, but co-running them together could exceed the bandwidth limit. We need to analyze the memory bandwidth requirement of co-running. Third, CPUs and GPUs have different preferred memory access patterns. Current methods do not consider these complex situations of shared main memory in the integrated architectures. The third challenge comes from the adjustment for dynamic workload. During stream processing, stream data are changing dynamically in distributions and arrival speeds, which is challenging to adapt. First, workload change detection and computing resource adjustment need to be done in a lightweight manner, and they are critical to performance. Second, the query plan may also need to be updated adaptively because the operator placement strategy based on the initial state may not be suitable when the workload changes. Third, during adaptation, online stream processing needs to be served efficiently. Resource adjustment and query plan adaptation on the fly may incur runtime overhead because we need to adjust not only the operators in the DAG, but also the hardware computing resources to each operator. Additionally, the adjustment among different streams also needs to be considered. Now, let's look at our solution, called FineStream. We propose a framework called FineStream for fine-grained stream processing on integrated architectures. The overview of FineStream is shown in this slide. The workflow of FineStream is as follows. When the engine starts, it first processes several batches using only the CPUs or the GPUs to gather useful data. Second, based on this data, it builds a performance model for operators of a query on different devices. Third, after the performance model is built, the dispatcher starts to work, and the fine-grained stream processing begins. Each operator shall be assigned to the cores of the CPU or the GPU for parallel execution. Additionally, the workload could be dynamic. For dynamic workload, query plan, adjustment, and resource reallocation need to be conducted. We first study the topology. The query plan can be represented as a DAG. In our paper, we concentrate on relational queries. We show an example in this slide, where OPI represents an operator. OP7 and OP11 can represent joins. We follow the terminology in compiler domain and call the operators from the beginning of the operator after join to the operator that merges with another operator as a branch. Hence, the query plan is also a branch DAG. FineStream involves three optimizations. The first optimization is branch co-running, which means that the independent branches can be executed in parallel. We use the example in this slide for illustration. Assume that the time for different branches is shown in the slide. If we co-run the three branches simultaneously, then The execution can be partitioned into 3 stages with different overlapping situations. If the required bandwidth for stage I exceeds the system maximum bandwidth, we can perform a branch scheduling optimization. The second optimization is batch pipeline. We can also partition the DAG into phases and perform co-running in pipeline between phases for processing different batches. For simplicity, in this part, we assume that the number of phases in the DAG is 2. Please note that when the platform has enough resources, the pipeline for operators can be deeper. We show a simple example in this slide. The operators in phase 1 and the operators in phase 2 need to be mapped into different compute units so that these 2 phases can co-run in pipeline. Figure B shows the execution flow in pipeline. When FineStream completes the processing for batch 1 in phase 1 and starts to process batch 1 in phase 2, FineStream can start to process batch 2 in phase 1 simultaneously. Phase 1 and phase 2 can co-run because they rely on different compute units. The third optimization is for handling dynamic workload. In FineStream, we use a lightweight dynamic resource reallocation strategy. When the workload ingestion rate of a branch decreases, we can calculate the reduced ratio and assume that such proportion of computing resources in that branch can be transferred to the other branches. We use an example in Figure 8 for illustration. In Figure A, 19% workload after operator OP1 flow to OP2. When the workload state changes to the state in Figure B, part of the computing resource associated with OP2 shall be assigned to OP3 accordingly. We present the system execution flow in this slide. Thread 1 is used to catch input data, while thread 2 is used to process the cached data. The detailed execution flow is as follows. First, when FineStream starts a new query, the dispatcher executes the query on the CPU for batch 1, and then on the GPU for batch 2. Second, during these single-device executions, FineStream conducts online profiling, during which the operator-related data that are used to build the performance model are obtained, including the CPU and GPU performance and the bandwidth utilization. Third, with this data, FineStream builds a performance model considering branch co-running and batch pipeline. Fourth, after building the model, FineStream generates several query plans with detailed resource distribution. With the generated query plan, the dispatcher performs fine-grained scheduling for processing the following batches. When dynamic workload is detected, FineStream performs related adjustment. For the operators in FineStream, we reuse the operator code from OmniDB. Please note that the goal of this work is to provide a fine-grained stream processing method on integrated architectures. Let's look at the evaluation. We perform experiments on 4 platforms, 2 integrated platforms and 2 discrete platforms. The baseline is a bulk synchronous parallel model, which is Sava in our experiment. We use 4 datasets in the evaluation. The first dataset is Google Compute Cluster Monitoring, which emulates a cluster management scenario. The second dataset is Anomaly Detection in Smart Grids, which is about detection in energy consumption from different devices of a smart electricity grid. The third dataset is Linear Road Benchmark, which models a network of toll roads. These traces come from real-world applications. The fourth dataset is a synthetically generated dataset for evaluating independent operators, where each tuple consists of a 16-4-bit timestamp and 6 32-bit attributes drawn from a uniform distribution. We use NAC queries to evaluate the overall performance of the fine-grained stream processing engine on the integrated architectures. For example, for the first query, we select timestamp, category, and CPU information from test event and group by category. Let's look at throughput. We explore the throughput of FineStream for the NAC queries. Result shows the processing throughput of the best single device, SABA, and FineStream for these queries on both the A10-7850K and Ryzen 5 2400G platforms. FineStream achieves the best performance in most cases. This slide reports the latency of different queries on the integrated architectures. In this work, latency is defined as the end-to-end time from the time a query starts to the time it ends. FineStream has the lowest latency among these methods. We show the relationship between throughput and latency of both FineStream and SABA in this slide, which shows that queries with high throughput usually have low latency and vice versa. We further studied the CPU and GPU utilization of SABA and FineStream and use the A10-7850K platform for illustration, as shown in this slide. In most cases, FineStream utilizes the GPU device better on the integrated architecture. The current GPU on the integrated architecture is less powerful than the discrete GPU. The discrete GPUs exhibit 1.8 to 5.7 times higher throughput than the integrated architectures, due to the more computational power of discrete GPUs. However, the integrated architecture demonstrates lower processing latency compared to the discrete architectures when the data transmission cost between the host memory and GPU memory in the workload is significant. FineStream on integrated architectures shows a high price-throughput ratio compared to SABA on the discrete architectures. This slide shows the comparison of this price-throughput ratio. On average, FineStream on the integrated architectures outperforms SABA on the discrete architectures by 10.4 times. We also analyze the energy efficiency of FineStream and SABA. On average, FineStream on the integrated architectures is 1.8 times energy efficient than SABA on the discrete architectures. Let's look at the conclusion. We propose the first fine-grained window-based relational stream processing framework that adopts continuous operator model and takes the advantages of the special features of integrated architectures. We develop lightweight query plan adaptations for handling dynamic workloads with a performance model that considers both the operator and architecture characteristics. We evaluate FineStream on a set of stream queries to demonstrate the performance benefits over current approaches. Thank you.